Welcome. Okay. All right. Hello, everyone. Welcome to Scienceholic's 2023 webinar, A Journey into the World of Chemistry. Thank you so much for attending today's session about using carbon dioxide as a building block for necessary compounds. And we're so excited to welcome Professor Barecka today to talk about her experience in teaching and research. My name is Anshi, and I am the host of today's webinar, and we will have lovely Emma as our co-host, and she will be helping out in the chat. Okay, before we start, let me give a brief introduction on who Scientoholic is. We are a youth nonprofit that aims to introduce intricate scientific concepts in a manner that is fun and comprehensible to teens. We also provide volunteer and leadership opportunities to teens all over the world, including those who have English as their second language. Our main mission is to serve as a free resource for students who want to learn more about various STEM topics. Other than this webinar branch, we also publish seasonal magazines. Our most recent one is published in April, and it's a biology-themed magazine, and it's our 7th edition. You can check it out on our website after this webinar. Without further ado, please welcome Professor Barecka again. Professor Barecka, would you mind introducing yourself to us?
Of course, and first of all, thanks again for the introduction. And I have to say that when I was invited, and I then start to look at different Scienceholic materials, like your website and the journals that the articles that you're publishing, I was really impressed by the quality of the articles, by the idea of the outreach. So fantastic job, and please continue to do so. I think it's an amazing initiative, and it's a great pleasure to be speaking to all of you. So yeah, just to very quickly introduce myself. My name is Magda Barecka. I'm an assistant professor of chemical engineering and chemistry and chemical biology at Northeastern University in Boston. So Northeastern is a university which is very centrally located, and we have a very strong focus on having an impact on the real world. So that's why our students, they spend a lot of time actually getting practical experience working in companies for a couple of months. And this is also why we researchers are very focused on identifying research subjects that really need urgent response, urgent solving, in order to enable us sustainable growth and achieving all sustainability goals. And both myself and my journey. So I was born and raised in Poland, and this is where I also got my undergraduate education. And after that, I started to different international activities. I got my PhD degree in TU Dortmund in Germany. And this is the area which has a very strong footprint of chemical industry. And my PhD thesis was in chemical engineering, and I was working on optimization of these large-scale processes which deliver chemicals that we use in different areas of our everyday life. And because my work was very applied, I later joined a company where I transferred the method that I developed during my PhD thesis, and then I worked also on other industrial projects. However, at a certain point, I realized that I would really like to have more impact on solving real life problems. And I would like to do things which are maybe a little bit more risky because they're very innovative. And that's why I decided to move back to academia. And I accepted a postdoc position at University of Cambridge Research Center in Singapore. So I moved from Switzerland then to Singapore. It was an amazing move, and I really enjoyed very much living there and doing research. And this time enabled me to really focus on scientific challenges, which I find most exciting. And I developed a program to start my own research group here at Northeastern University in Boston. So this was my journey. I think we'll be partially like coming back to these topics as we go through the questions that was prepared by the panel. And I just wanted to encourage you tonight to ask any questions that you might have. My mission here is to be support for all of you in terms of also thinking what you would like to do, what you find exciting. So please feel free to ask about anything related to to my scientific journey, career, research topics. I'm glad to give you any support that I can.
Thank you for the introduction. Okay, attendees, This is just a reminder to put your questions in the chat if you have any. We'll go over them as we get them, or if we can't answer them right now, we'll try to answer it at the end of the webinar during the live Q&A portion. We'll start asking questions now, and we'll first ask questions related to academics. So our first question is, what made you interested in chemical engineering, chemistry, and chemical biology?
Yeah, that's a great question. I have to say that there was nothing in my life that was really like this one life-changing event that made me decide that I want to study chemical engineering. It was rather a very gradual process of asking myself questions of what I'm interested in and narrowing down which is the path that corresponds best to my interest. I think that everything started just with thinking about environment, and just like early, like being a kid and a teen, I was observing a lot of different environmental impacts around in the place where I was growing up, and I was actively asking myself what we could be doing better. And I remember very much the first time when I was exposed to the idea of the climate change and like start to understand all its potential consequences. So at the first point, I thought that I would like to study environmental science as a way to understanding what we can do with climate change. But then as I started to do research about what environmental sciences are, I realized that actually engineers might have an opportunity to be more impactful in that space because they're creating technologies. And from there, I found out that actually chemical engineering gives me the knowledge and the tools which are really necessary to solve problems related to environment. So as I said, it was like a multi-step path of looking at different disciplines and really finding what corresponds best to my own values. And currently, I'm a professor of chemical engineering and chemistry and chemical biology, meaning that I'm appointed at two different departments at the university. And this is because the research I'm doing right now is very interdisciplinary. So this is something that does not fall into the very strict categories of just one discipline, such as chemical engineering, but actually lots of things that we're doing, they're very related to research in chemistry space because we're looking at new catalysts, development of new catalytic pathways. So that's where my joint appointment comes from.
Yeah, so I feel like sometimes people can get stressed. We're supposed to know to, but a lot of times it's more like gradual. Like as we get older, we see these problems and issues around us, and that's what helps us find our passion in life. Okay, our next question is, what encouraged you to start teaching?
In terms of teaching, I also think that this is something that kind of organically evolved around my role. So as I was getting more and more interested in doing research, I was looking closer at what does it involve in an academic setting. And I found that an important part of an academic role is actually teaching. So I was definitely asking myself, like, how would I interact with students when I'm teaching? What should I do to be a good teacher? And what I found out is because I really enjoyed the one-to-one mentorship interactions that I have with the students that I was mentoring in the lab, I thought that I would just be able to use the same strategies that I used and the same mentoring, but just to expose it to a larger group and be able to interact with more students and provide mentoring to more students. And I think that just making this link that actually teaching is very close to mentoring was something that made me definitely much more interested and passionate about teaching. And now when I started to teach larger groups of students, I realized how much the teaching activity really brings also to my research, because all the interactions that we have as professors with students, they give us a lot of inspiration, a lot of thinking. It's a really like a two-way street. It's a two-way interaction. And this really brings a lot of value to everything that I'm doing. So I'm very glad that I was able to make a good link between mentoring and teaching and explore this on a daily basis.
It's great. So what is one of your favorite topics that you loved learning or teaching about?
Oh, it's a very good question. Difficult just to point out one, but definitely something that I would like to start with is actually photosynthesis process. So the photosynthesis process, it's something that inspires me a lot Because I see it as a very wise way to produce chemicals, because photosynthesis uses only sunlight, water that the plant is able to draw itself from the ground, minerals that the plant is drawing itself from the ground, and sunlight, which is available in an intermittent way. So the sunlight is not available all the time in the same manner, it changes, but still the plants know how to adjust and still know how to produce the chemicals that they need to grow. So this is something that I'm always kind of circling back in my research, because this is just an example of something very, very smart, very sustainable. And what is very interesting, something that we don't really deeply understand. There are still lots of question marks about photosynthesis. So actually what we're doing in my lab, lots of technologies that we develop in a way are mimicking this photosynthesis process, right? So we're trying to develop the very same functionalities that plant has, but in a reactor that we actually can assemble, manufacture, produce, and use to synthesize chemicals. So definitely one of my topics is photosynthesis, and I gave several guest lectures on this topic, and this is also part of the elective class that I'm giving on carbon capture and utilization. And it's something that I always talk about with my students. We kind of have this photosynthesis theme coming back in lots of our group meetings and our discussions. So that's my number one, but I also would love to tell you a little bit about capstone design. So capstone design, this is the class which I'm teaching usually in the fall. And I find it super interesting, because this is the class where students who are about to graduate, is usually their last semester as chemical engineers. They're exposed to an activity of designing an entire chemical production process. But chemical production process does not necessarily mean it's a chemical in the way that we imagine it. So I don't know, it's something that you can see in any of your cosmetics or in any of the cleaning agents. It doesn't really have to be a chemical as such. It can be also a process which just involves chemical engineering steps. So for example, it can be design of carbon capture units. It can be a design of a more sustainable way to obtain cosmetics. It can be a design of a more sustainable way to create nanoemulsion for some kind of pharmaceutically active ingredients, pretty much anything. But the idea is just that students can think about what they learned during these 3-4 years and really distill all this concept in one design, and they have an absolute freedom to decide whatever they want to do. And the ideas that they have are just amazing. They're very creative, very innovative, and I really like the interactions that we're having. So this class I'm particularly passionate about, just because of the opportunities for creativity that it opens, and also the opportunity that I have to work very closely with students.
That's great. I actually really love your view on photosynthesis, because I feel like I learn photosynthesis every year that I have biology, but a lot of kids don't really feel the beauty of it because it's very obscure, and it's actually really cool how plants are able to sustain life without having to move or do a lot of things that we're able to do.
Yeah, exactly. And they do everything on their own, right? Don't really rely on something external.
Yeah, it's just, wow, I wonder how they do it. Our next question is, how can someone follow your path? Is there anything that you recommend doing or opportunities that should be taken?
Oh, it's a very, very, very good and very broad question. So I think first of all, I think it's really challenging to decide what is the path that you want to follow. So that's a kind of the first tranche, I think, that we all experience to a lower or higher extent. For me also, it was not something obvious from day one that I want to be a professor of chemical engineering. As I already mentioned before, there were kind of question marks and trying different things which were involved on getting to through this path. So I think that actually to follow my path, so the very first step that I would recommend is really trying to understand what is really something that represents lots of value to you, that really resonates, what is important to you. So what is the thing that you can think about when you wake up in the morning very early, you're tired, it's cold outside, there are all these unpleasant opportunities, but you still want to wake up, start working, and start putting your energy in this. Identifying this thing is definitely very challenging because we're of course we're always exposed to lots of ideas around us. We see what our peers are interested, and we sometimes feel like we should be interested in the very same thing. We are not necessarily interested. Then we're missing some role models, and we don't know who to ask questions about. So I would just like to encourage you that if you feel that there are things that you might be interested in, and maybe this is science, it's okay to have all these doubts and to question and to like think, do I really want to do this? And it's okay that those who are around you might have a very different opinion, and be sharing this opinion with you. It's completely okay. But what is really important is for you is to figure out what internally really motivates you to work. Because if we are doing what we really love, then we can absolutely excel at it. So that's one thing that I can say. And I would definitely say that the first step to following this path would be doing your best in understanding what you really, really want. And sometimes to understand, we have to try different things, and we have to figure out that we don't like what we tried. And this is also completely fine. So I would recommend that, if any one of you, if you think that maybe science is something that actually I would like to do, one of the things to do is maybe just to try like baby steps, try to get involved like in a project on a smaller scale, just to get a little bit of sense of what does it mean. I know that different stages of education and career, there are very different opportunities available. I am, for example, currently mentoring one high school student who is just spending their holidays time on doing research in CO2 electroreduction space. So I'm sure that there are opportunities at very different point when you can just get the flavor of what science means and if you like it. Definitely, if you're thinking about going to college, in college there are opportunities to do undergraduate research, which I would very strongly recommend to everyone, because this is a better exposure to research when you can actually go to the lab and ask a professor to engage you in a project that you're interested in, get some wet lab experience, as we call it, and also work with graduate students who are just have a little bit more experience than you. But I think they're great mentors because they very recently went through the very same path. So that's a great interaction. I always try to pair my undergraduate students with graduates so they can be mentored and work closely. So step one would be to think of like what you really want to do. Step two, identify opportunities to do some research early on, even if it won't be a complete project, if it won't be something that you can have a poster presentation about. It is just a matter of this experience for you. And the third thing that I would recommend also to everyone, as much as you can, I think that finding an opportunity to study or to spend some time working or studying abroad or in a very different environment that you're growing up, it's something that creates lots of value. So I recognize maybe it's a redundant advice because maybe you already have a lot of international students of those who already went through this path. But if any of you didn't, I would definitely recommend it. I think that for me as a scientist, the fact that I was living in very different countries with very different cultures, actually it's helped me a lot to create the science that I'm working on, because it just gives you an opportunity to think differently about everything. And what we really need to be a good scientist, we need to question everything, right? Because things are not established. We have to find answers to the questions which are currently not well understood. So definitely exposing yourself to anything that gives you inspiration is very, very helpful. I hope this answered the question. It's extremely broad, and please feel free to ask me anything that you would like to know about it.
Thank you. That was actually a really good answer. I feel like especially like these days we're pressured to, achieve success, and it's always this clear-cut path, like going to an Ivy League and then getting the same jobs that, pay more. So I think it's really fresh that you like recommend students to find what they love and to take it slowly and to experience like going abroad instead of going to this college and becoming a doctor or whatever. So I think it's really nice that your thoughts on pursuing your passion is more important.
Yeah, absolutely. Maybe one thing that you just inspired me to add to this question is that I also recommend not to ever think that it's too late to change something, because I think that every year we're told that you have to take decisions regarding your professional career like very early on, and whatever you decided early, you can't change it because then your career won't be that smooth. And I think that's not true. I actually went to the industry, I discovered I don't really like it, and I went back to academia and still was able to become professor at a very similar time as my colleagues who were only in academia became professors. So I really don't think that there's any point where it's too late for you to change if you feel that you really want the specific change to happen.
Oh, your words are so reassuring. I feel like, especially because I'm applying to college now, it's like the stress is really coming in right now.
Yeah, I can imagine.
Yeah. So going along with it, do you have any words of advice or encouragement for students possibly looking into your field, or anything you wish someone else, like a mentor, had told you before you started your journey?
Yeah, that's also a very good question. So I would just like repeat once again what I just said. It's never too late to change. And if you really want something, if you really want specific career, you can get there at any stage of your life. It's just a matter of creating a strategy which works wherever you are. And something that also I think is very helpful, all of us, regardless of our age and where we are in our career, we need mentors. And a good mentor is not someone who tells you you should do A and B, but a good mentor is someone who makes you think and who makes you understand and discover what you want. And I think this is a very important difference, which myself, I was not necessarily seeing when I was younger. And I was probably a little bit kind of expecting that someone will come and tell me what I should do and I will do it and I will be happy. And it's not that easy. Not because people don't want to help, but because we're all individuals, we're all very different, and everyone has a different recipe for being successful and being happy. So I recommend everyone to think about who can be your mentor, who will just help you in this process of thinking, and who will also be able to give you some support and reassure you that what you're doing is good. Because we all need it. We all need to hear that what we're doing is good. And sometimes you might have a professor that you will have a closer relationship with who could be this mentor, but the mentor does not necessarily have to be more experienced or older than you. It can be your friend, but it just needs to be someone who really wants to understand you, and that you can have a conversation with from time to time. Maybe if it's someone who, let's say it's just a couple of years older than you and just went through the path that you would like to go, and then this is like a natural match that you might want to talk to. But if this is someone who doesn't have experience, I would still recommend just to have in your mind a mentor, because it also gives you responsibility of thinking, okay, I have a mentor, I should talk with my mentor. So what I will talk with my mentor about? Well, how I am progressing in my professional development, how I'm progressing in defining my goals onto moving towards the achievement of my goals. So having a mentor also creates this kind of responsibility for us to think about our path and about ourselves and like how we are doing. So yeah, I truly believe that mentors are so important, and I wish this is something that I knew a little bit earlier in my career.
Thank you. It's a wonderful answer. Okay, now we're going to our next section of questions which pertain to your research. Could you give us an introduction to your research in your lab?
Yeah, absolutely. So my lab works on development of new methods to synthesize chemicals, which use, and these methods use carbon dioxide as a source instead of waste. So we are converting carbon dioxide into chemicals. And the big idea here is that we do not want to rely on fossil fuels anymore. We want to be able to synthesize all the chemicals that we need just for carbon dioxide in the air. And of course, as our population is growing, is actually projected to grow a lot, we will continue to need a lot of chemicals, and our demand for these chemicals will be very high. We need these chemicals for food industry, for pharmaceutical industry, for packaging, for hygiene. So there's a number of sectors where we need them. We need them to maintain certain quality of life. We can't just resign and stop using them at all. But there's a big problem that we're currently producing all of this from fossil fuels. So the focusing of my lab, it's let's do something to stop this situation, and let's produce everything that we need from carbon dioxide in the air. So this will be kind of like a circular economy. Of course, this is not so easy because carbon dioxide is not a molecule which is easy to convert. Therefore, we need to put energy in this process, and we want to source this energy from renewable sources. So basically, we want to use renewable electricity. So the technology that we use is called electrochemistry, because we are using electricity to convert CO2 into different chemicals. And now what is different about my lab in comparison to other labs that are somehow working in a similar space is that we are very focused on enabling the use of this technology in the future in the industry. So we are right now working with the lab, we're using very small reactors, but our mission and our ambition is to do the discoveries which are necessary to make this technology something scalable and something that can be adopted by the industry. So we are focusing very much on basic science questions that need to be answered to allow for these transitions. So I think we have a kind of like a very I would say like very close connection to application, to practicality. I also have different collaborations with industries, which gives us hints what is really necessary and what we should focus on to make these things applicable. So this is the very broad idea. Of course, within this paradigm shift of electrochemistry and using CO2 feedstocks, we have a number of very different projects, but the main mission is to enable us to source all the chemicals from air and don't use fossil fuels.
So the goal is to become more like plants, right?
Yeah. Yes, you're right. Very
So
right.
what kind So what kind of electrochemical experiments have you guys been able to perform, and what can they do and what do they do?
Yeah, that's a great question. So there are very different electrochemical experiments that we're running because electrochemistry can be used for a number of purposes. We can use electrochemistry to synthesize new materials, like new catalyst itself. We can use electrochemistry to convert CO2 into useful chemicals. I'll just give you a couple of examples. So one of the experiments that we have been running, we were using electrochemistry to capture carbon dioxide from air and just concentrate it. Okay, so we're just looking at this step. We didn't look at about how to convert it into something else, but how to capture and concentrate it so that it could be sent for the underground storage. So this one kind of experiment, which was driven by one of my undergraduate students, who, even though she was working at this time on her co-op, she was working in a company. She just wanted to do so much this research after work. So we started the projects where the novelty of this approach was about using reactors with a very specific microstructure, which enable us to do it much more efficiently than by using other methods. So this is one example. Another example was another student of mine was interested more in the synthesis of materials. So she wanted to use electrochemistry to create catalytic materials based on copper. But actually, for this very specific experiments, there was no reactor existing that we could use. So the very step of this part of research involved actually creating the 3D designs of reactors and 3D printing these reactors, assembling these reactors, and then running the reaction. So this was a collaborations that we have with students from mechanical engineering, because we need a little bit of knowledge of mechanical engineering to actually design and 3D print reactors. But this was successful, and actually the paper which presents the design of the setup is now under the review, and I think will be published very soon. So I'm very happy for my graduate students to almost have a paper after just 1 year of working at the university.
That's wonderful. Oh my gosh. Sounds so interesting.
Thank you.
So what kind of different technologies are you and your team developing to help, make these experiments happen?
Right. So I think this relates a little bit to the last question. So in terms of technologies, as I said before, we mostly focus on CO2 electroreduction. So we want to use renewable energy to convert CO2. And this is kind of our core technology right now. So maybe I will focus a little bit on the projects where we do the utilization of CO2. So we go from CO2 to different products. So to achieve this, we first of all, we prepare our catalyst, as I mentioned, by creating the new methods. We mostly use copper-based catalysts. And then we operate this reaction under the conditions which we are currently optimizing from the chemical engineering perspective. And how our experiments effectively look like is that we are putting this catalyst in a kind of like a sandwich reactor. We're applying flow of different liquids, the flow of gas. We're creating the conditions which we know are best for this reaction. We're applying electricity, which, right now in our lab, is just the electricity from grid, but in future, this is something that will be used from renewable sources. And then the part that I find personally most exciting is that we connected to the analytical equipment, to mass spectrometers, which allow us to see in real time the products that we're obtaining from conversion of carbon dioxide. So in real time with this equipment, we can see we're flowing CO2 inside of the reactor, and what is exiting the reactor just like a second later after it entered, it's, for example, a combination of ethylene and hydrogen and just some unreacted carbon dioxide. So we see this change happening in the real time. And in terms of product, we like very much to focus on products such as ethylene, ethanol, propanol, just because these specific molecules are very useful for the chemical industry. So if we find ways to synthesize these molecules from CO2, we expect that it will have more impact on decarbonizing chemical manufacturing.
That's so cool. It's amazing how science can develop so quickly in such a short amount of time to help our industry. Okay, so our next question is, how is carbon dioxide able to be used as chemical building blocks for other necessary compounds?
Oh, that's a wonderful question. And there's actually millions of ways in which it can be used. So maybe I'll start with this, that actually, if you think about the chemical composition of different chemical composition of chemicals, right? It's a repetition. But if you look at composition of, for example, any kind of cosmetics that we're using, cleaning agents, etc., majority of the compounds that we see there, they almost all have carbon, and basically this carbon in almost all cases could be obtained from carbon dioxide in the air or in different biogenic sources, such as, for example, biogas. So in principle, there is no limitation in terms of where we could use the carbon, which is obtained from CO2 conversion. The only difference is that sometimes for some applications, it might need more conversion steps, so more of catalytic processing in between, but we could use it pretty much everywhere. So a very, I think, a simple and good example are all kinds of hard plastics. So for example, if you think about materials from which typical luggage that we use when we travel is made from, This is something that could be replaced by high density polypropylene. And this is something which basically has lots of carbon, and there already exist methods in terms of how to obtain these materials from carbon dioxide. So now the challenge with converting carbon dioxide to any chemical that contains carbon is that carbon dioxide is a very stable molecule. So if a molecule is from thermodynamic point of view stable, it's just difficult to convert it to anything else because we need to put in lots of energy to the process because it just doesn't want to convert. So what we focus on as scientists is to find a catalyst which makes this reaction easier, which basically makes the dissociation of the bonds of this molecule easier, so this carbon inside of carbon dioxide can bond to something else, to something useful. A very easy step to do is to go, for example, from carbon dioxide to carbon monoxide. But this carbon monoxide is already something much more reactive that we can easily use for another conversion step. So with use of catalysts and with use of renewable electricity, we can convert carbon dioxide to basically any other chemical building block. The question is always will be the numbers of the step that we need in between. And as I said, for some cases, it can be a little bit longer. So something I wanted also to highlight that, of course, electrochemistry, it's not the absolutely unique method to convert carbon dioxide. There are also other methods to do it, and we need scientists to develop all of them so that we'll have different opportunities to synthesize chemicals in a more sustainable way. So in addition to electrochemistry, there are also methods that are, for example, involve the use of plasma to convert carbon dioxide. There are also methods which involve the use of enzymes. And actually, we're also using enzymes a bit in my lab, but we are combining enzymes with electrochemistry, so to make it at the same time. And another thing that we are actually also trying, and I find it very exciting personally, is to realize this process of converting carbon dioxide into chemicals, not by using renewable power, but just directly using sunlight irradiation. So again, circling back to photosynthesis, something getting closer to photosynthesis scheme. So yeah, there is a very broad variety of methods. And as a scientist, I really believe that we should be working on all of them so that we have different options to become more sustainable. And I also try to support other researchers working on other methods as much as I can, because we really need all to work together on this.
That's great. Thank you. And how does this impact our environment, and in what ways will this improve sustainability in our daily lives?
Right, this is a very, very important question. So maybe one thing that I really would like to emphasize here once again is that the availability of use of different chemicals is really important for our health, for our hygiene, and for basically being able to continue the growth in the way that we are used to. So we know that we need all these chemicals, and right now you can think that any plastic bottle that you're using, any shampoo, any basically product that we have around us, its production was associated with the use of fossil fuels. So there was a lot of CO2 emission that happened to have these products in our hands. So finding another ways to synthesize chemicals basically takes this problem away. So what impact it will have on our environment, I can even give you numbers. So right now, the CO2 emissions from the chemical industry are around 8 to 10 gigatons of CO2 per year, gigatons of CO2, right? So this is really a lot. And this is something that we could completely omit if we have better ways to synthesize chemicals. So the impact that I hope to see on the environment is that, first of all, we don't have the CO2 emissions. So we are not contributing in the same way to the intensification of climate change. And if we don't contribute to the intensification of climate change, well, this affects everything, right? Because we know that climate change is not only rise of temperature and rise of sea level, but it's also drought and wildfires in other places, and tons of consequences that we see. So this allows us to do our best to minimize and prevent this thing from happening. So this is one thing. Another thing, which I didn't actually mention during this conference yet, is that the technologies that we're developing, CO2 electroreduction, as I said before, works in a kind of like a sandwich reactor. So literally the reactors that we have in the lab is like a 3-layer sandwich. And this kind of reactors are much easier to use on a larger scale, because basically if you need more chemicals, we do something which is called numbering up, which is like use more layers, right? And this is something very easy to adjust to a larger scale and to a higher need, higher demand from chemicals. And the only connection that you need to make it work is the connection to renewable power, right? So this opens a great opportunity of synthesizing chemicals in place in the world that do not have like all the infrastructure, but maybe there are populations that really need these chemicals. So we could just put these sandwich reactors right there, have, for example, a photovoltaic panel that provides electricity, and synthesize things in the place where they're necessary. So I think it's maybe not necessarily impact on the environment, but it's more an impact on human well-being and on human health, which I think this is something that also could be improved with these technologies. So, and lastly, I think that, like it will of course take time till we can use these things on a large scale and reduce all these emissions. But what I'm personally very passionate about, and I think this is also something that really resonates with what my students are thinking, at least we know that we're doing our best to get there, because we put our everyday efforts in achieving carbon neutrality.
So is there ever, I know you mentioned using this to help like in a big scale kind of manner. Is there like, are we ever going to be able to have it like in our daily lives where like even like it helps reduce like an individual's carbon emission? Or is it like in the industry where while they're making products like plastics, they'll reduce their carbon usage?
Oh yeah, that's a good question. I think that in terms of this time scale, it's definitely something that I see happening like in 20, 30 years, like having this on a very large scale. I mean, we'll not have it on large scale tomorrow. We'll not have it like in 2, 3 years, but there's definitely something that I see feasible in 20, 30 years. Looking at like how different industries have evolved, we can have a change happening in that time. We just need to be sufficiently motivated for change. But I think that now the understanding of climate change and all its consequences, it starts to be more solid and more recognized on different levels. And something that we also think a lot in my team is how to make these technologies economically viable. So in order to implement them, we will not only rely on like people's willingness to do something good for environment, but there will be actually an economic incentive to do so, because it will just cost less, and it will be, or will have like another kind of benefits, which can be quantified. So we found different specific applications when these technologies can be economically viable, and we use them to talk with our industrial partners and get more momentum for these things to grow. So definitely I think in 30 years lifetime, I envision this being used on a large scale. And coming back to the second part of your question, if it's something more used for reduction of personal carbon footprint versus industrial, I think it's very difficult to really draw the line like between personal footprint and industrial, because I would say this technology is being used by the industry, so their products are more sustainable. But then there's a second part of the choice of the customer. So when the customer is buying the product which was synthesized from carbon dioxide in the air and not from fossil fuels, well, then you're actually reducing your carbon footprint. So I think its definition is maybe like a little bit challenging to draw like a very strict line where industrial footprint ends, where personal footprint starts. But the way that I see this technically happening is that these are the industrial partners which are buying these electrolyzers from startup companies that will be developing these, they're putting them on their production site. And as a result, the products that they will be selling have a reduced carbon footprint. And hopefully this is something that everyone will want to buy as well, because we need this understanding.
Yeah, thank you. Okay, so now is our live Q&A portion. If any of our audience members has any questions they would like to ask, feel free to put them in the chat. Okay, so we have a question from Katie. She wants to know when you should start finding your mentors to help you on this path towards your.
Yeah, well, honestly, I would say now. It's absolutely never too early to find mentors. And it also could happen that you find a mentor, you start having conversations with them, and maybe during after some time, your goals, your understanding of your goals might change, and maybe you can find out that you need another mentor, and it's completely fine. But I would say the earlier that you identify someone who can be the mentor, the better. As I said before, this person definitely shouldn't be telling you like what you have to do, because this decision must be yours. It should be someone who will just support you in your process on working and thinking what values are important to you, and then like how you want to go about creating some goals and strategies based on these values. So this, I would recommend to start working with mentors as early as possible. And also when we start to work with mentors, we start to realize what we really expect from the mentor. In the very beginning, it can feel a little bit weird, and that's absolutely fine. So I recommend definitely starting early. Actually, I think it should be soon published online. I had a great pleasure to be selected for the Future Leaders Award from the American Chemical Society. And within the team of this awardees, we prepared an article on mentoring and how to find a mentor. So I think this should be available online quite soon. And whenever it is, I'm also very happy to share, because it has like a list of different, very specific advice, like what to do, when to do, what you should ask your mentor for.
That's great. Congratulations.
Thank you very much.
Okay.
It was a very good question, Katie.
Okay, so I don't think we have any more questions. So okay, so that is the end of our webinar. These are our ScienceHolic social media handles, so please give us a follow if you're interested. YouTube is where we're going to publish the recording of all of the webinars that we host, and you can also find them on our website, and Emma will paste the links in the chat for you. And attendees, if you're interested in working with us, here are some various ways you can do so. Emma will also post some more links for that. There are 6 teams, and you can also submit an article to us if you want to. If you want a low commitment way to help us, you can become an ambassador. And lastly, please join our mailing list for updates on new articles or magazine releases and webinar updates if you're interested. You can find our Discord on our Instagram page. Here are our partners for the webinars, as well as the magazines that's coming out very soon in September. Please note that there will be 2 volumes of the chemistry theme magazine this time, so stay tuned for that. And lastly, thank you all so much for attending this webinar. And to Professor Barecka, thank you for your time again. Emma will be posting her email into the chat, so feel free to email her and ask more questions if you have them, or if you're interested in her research or maybe her teaching and her journey to that. And please tune in at 7 p.m. Eastern Standard Time tomorrow for a webinar about chemistry in forensic and investigative science. Thank you, guys. Have a nice rest of your day.
It was a pleasure.
Yeah, thank you so much.
Here. you.